Oops. Well, welcome back, everybody. You guys can hear me?
Yes.
Okay, great. So we're back for really doing covering our last 2 units of the semester. So today I'm going to begin with Unit 3, which is going to cover chapters 29, 30, and 31. Okay. And if you see on the board there, the next exam is May 4th. So I'm hoping that that gives us a comfortable pace for this unit. It is a unit like Unit 2. So it is a challenge. The one advantage you have is that because of the complexity of some of the equations that are involved here, that I'm more limited as to what I can ask. Okay, so that helps you folks. I've been thinking about this. Folks came to office hours this morning regarding the lab, and there were some things. I apologize. I omitted from the lab. The lab is fairly new because we've been online, and I've been making changes. But I guess at the end of last semester, I didn't make all the changes I should have. In the lab, I talked about running the experiment at 6 volts. The handout you got said 9 volts. I was reading off the old lab. Whether you use 6 volts or 9 volts on the lab, that's perfectly fine. Don't retake any data. If you did it with 6 volts or you did it with 9 volts, I'm going to be fine with either one. Okay? So that's not a problem. The one thing, though, is I forgot to take out the statement about the uncertainties. Okay, and I said in the video, use the manual that came with the meter for the uncertainty. So let me go through that again very quickly regarding the uncertainty. So let's say you measure a resistance of 250. I want to go over this one again. 0.1 ohms. And the multimeter says that your uncertainty is 1% and 5 digits. This represents the uncertainty in the last digit. So this means that this last digit is off by 0.5. Okay. Aside from the 1%, this value can be either 250.6 or 249.6. In addition to that, there's this error due to the accuracy, and so we got to factor that in. So then you got to take 250.1 ohms times 0.01 gives you 2.5 ohms. And then you got to add this half digit to this. So your uncertainty is 3 ohms. And so you're going to write for the value of the resistance. Okay? Okay? So, yeah, so Vincent, that was a mistake on my part. I apologize for that. So I'm going to give you guys a couple of extra days to turn in the lab. Okay? I'll change after class. I will change the deadline so you can actually change the values. Okay? I'll give you guys till Thursday evening. I haven't graded, part of it I feel bad because I haven't graded the other labs anyway. So I feel bad in that sense. I was going to My goal was to grade over the break, but I got my second COVID shot, and that kind of knocked me out for a couple days. Okay. Yeah, so if you plan your second COVID, if any of you guys get lucky enough to get the COVID shot right away, just get the second one like over the weekend. First one doesn't bother you. Okay. But the second one can bother you. Depends. It bothered me. Okay. So I'll change the date afterwards, so you can turn in the lab on Thursday. Okay. So just be aware of this this calculation. And I was trying to go through and make the changes this morning, but I had so many meetings this morning that I couldn't do it. I'll try to send you something updated sometime this evening, so you can see what it should look like. I want to write an appendix with this statement in there too, so that everybody's clear on it. Okay, and like some folks said in lab this morning, and not lab, in office hours this morning, usually takes 2 or 3 go-arounds to get the lab cleaned up. Okay.
Professor, I was wondering, I think last class you said to do like one, like just one sample calculation for each thing.
For each table. I mean, yeah, for table 1, where you have to calculate the current and the uncertainty, you just show me one sample calculation.
Oh, okay.
For table 2, do this. I mean, you're still doing the same thing 3 times, but you're only doing one for each table, for each set of data.
Okay, because I did one for like each like question. It said to do one
for each question.
Yeah, like it was asking for like the uncertainty of the resistance and the voltage too.
Oh, that's fine. That's okay.
Okay.
Yeah. But when calculating your I for table 1, just show a sample calculation. And calculating your I for table 2, one sample calculation. Because finding the current through all 4 resistors, the calculation's the same. Why repeat the same thing? I'm assuming if you can do it once correctly, then you're going to be able to do it 4 times correctly. Okay. And after reading some of what folks said on Discord that they have 18 pages, I was surprised. I don't remember anything that long last semester, but 16. Okay, wow, that's fine. I mean, I'm not really grading. I'm grading on the content, but if it's that long, it's that long. It all depends on how big you write, how big your fonts are and stuff. So, and what kind of figures, the pictures you put in there, etc. Okay. So I'll have you guys turn it on Thursday. I really wanted to get the something graded over the break. I got the exam graded over the break. And since you guys did well, I was able to grade the exam pretty quickly. Okay. All right. So read chapter 29 in your book. And yeah, there is a section in chapter 30 I would like for you to read, because I'm going to say something about chapter 30 today. Just because of describing the properties of magnetic fields. We're going to talk about magnetic fields in today's lecture. The discussion is a little different than when we talk about electric fields. Okay, it's magnetic fields are a little bit more complicated. How they arise, etc. It's more complicated. So I'm going to use some hand waving, okay, as I describe magnetic fields. So let me go back a slide. These are the topics for part of the chapter. We're also going to talk about the force on a wire. So this first 4 items that you see on the screen or in the PowerPoint slide discuss basically the properties of a magnetic field and the force on a charge in a magnetic field. And then the lecture on Thursday, I will talk about the force on a wire in a magnetic field and talk about some applications, mainly the electric motor. And so on Thursday morning, I'm gonna talk about the actual electric motor lab. That should be hopefully a fun project for you folks. We'll see how we'll see how that goes. It's actually a little bit more fun when it's on campus because you have more testing equipment. Okay. I think this unit is probably the most interesting out of all the units in this course because of all the applications that exist for magnets. The applications in engineering. There's tons of them. What I show you here, I'll make this larger, is just a small sampling of all the applications that exist involving magnetic fields.
Magnetic field lines of a bar magnet. If we choose a Gaussian surface that encloses one end, we see that every field line that enters the surface also leaves it. Thus, the net flux through this surface is zero. This remains true if we expand the surface to enclose the entire magnet. If we move the magnet outside the surface, again every field line that enters also exits. Therefore, the net magnetic flux through any closed surface must always be identically zero. This is Gauss's law for magnetism.
So, you want to be the person in those voices?
A magnet produces a magnetic field that extends into space. A compass is itself a weak magnet that readily aligns to an external magnetic field. By moving the compass around the bar magnet, we can map out the bar magnet's field. The arrow defines the direction of the magnetic field. It points away from the magnet's north pole and toward the magnetic south pole. We represent the magnitude of the magnetic field by the number of field lines passing through a unit surface. Dotted circles on a plane mean the field lines are pointed directly at the viewer. X's on the plane mean the field lines are pointed directly away from the viewer.
Take a look at that convention in that figure, because we're going to be using that a lot in this unit. So those X's mean something into the plane of the screen or the board when I write on the board. And the dots with the circle represent something pointing out of the board. Now that we're going to be doing magnetic fields, we're going to be working in 3D. We got to think in 3D. That's the one big difference with magnetic fields as opposed to electric fields. What you saw in the video, and unfortunately I played it in reversed order, is that the magnetic fields are different from electric fields because the magnetic field lines always form closed loops, like you see in that first video. Electric field lines do not form closed loops. Okay, magnetic field lines form closed loops. In fact, a term you can say is that magnetic field lines circulate. They curve. Electric field lines don't curve, they diverge. And so from Calc 3, if you think about it, there's some operators associated with the electric field, and there's some operators associated with the magnetic field, or characteristics of them. So magnetic field lines, they curl around, they circulate. Okay, they form closed loops. They do have similar properties as compared to the electric field, and I'll get to them in a moment, but the one thing that's different is that they all form closed loops. And notice the field lines go from the North Pole to the South Pole. Okay, the field lines always go from the North Pole of a magnet to the South Pole. And there is no such thing as a magnetic charge. Thus, because of the fact that because these we don't have a magnetic charge, these field lines actually have to form closed loops. And if you integrate the flux through a closed surface, it's always zero. That's Gauss's law for a magnetic field. The flux through the magnetic flux through a closed surface is always zero.
A magnet.
Oops. Here's a couple more videos I want to show you.
We place a clear plastic sheet over bar magnets and sprinkle iron filings onto the sheet. The filings form patterns that indicate the presence of a magnetic field. Here, we place the opposite poles of two magnets near each other. The iron filings feel the influence from both magnets. When we place two identical poles near each other, the pattern looks very different.
So the iron filings gives you an idea what the field lines look like that are produced by a magnet.
We place.
Okay, so let me say a few things about magnetism. I mean, what causes something to be magnetic? And I put a couple nice videos in the modules about magnetism. They're short videos. They do a lot of hand waving too, because the details, in order for you to understand the details, you have to get to the quantum mechanical level. Okay. Question, what about the asymptote between the magnets? So are you talking about...
Like when you have two positive ends of a magnet near each other, isn't there a point halfway between them that where like their field lines push away from each other or whatever, don't?
Oh, like if you have a south pole here and a south pole here?
Yeah.
There will be a point in the middle where the field will be zero.
Right, yeah. Okay, thank you.
Yeah. So you won't see any field line there, right? The field lines will just avoid each other, right? In fact, I got to be careful. Field lines will do this, right? And the sum of them will give you a point in here where there's no field line.
Right.
Okay. And Brandon, I'm not understanding your question about polarization. Oh, what makes magnet? Okay, so there are two ways you can create a magnetic field, and they're both due to moving charges. They're basically due to moving charges. Okay. Number one is to run a current in a wire. If you run a current in a wire, you'll produce a magnetic field. Number two, then we have what happens within a permanent magnet. That's the harder one to understand. What makes iron a magnet? Okay. And yeah, Damien, all of this, magnetism is a manifestation of special relativity. So I should write that down. It's there because relativity is true. Okay? All right, so let's look at this at two levels. Okay, let's look at it first on magnetic material. Something ferromagnetic. Like a bar magnet. Okay, like these bar magnets. What makes them ferromagnetic? Now, this is not made out of iron. This is probably made out of a special material called alnico. Okay. And to understand this, you have to kind of go at the quantum level. Okay. If you have an atom, you have the nucleus of the atom, and then you have electrons going around the atom. Just the fact that the electron is going around an atom, you have a charge moving around, that will produce a magnetic field. A moving charge will produce a magnetic field. Okay? But if you have, let's say you have an atom with a filled shell like helium. Okay? The magnetic field due to the two electrons as a result of their motions are going to cancel. Okay? Any atom that has a filled shell, the resulting motion of the electrons is going to cause a cancellation of the magnetic field due to the atom.
Is that why they don't want to get any more electrons? Because there's like no net charge or field?
Well, the reason why you can't put any more electrons on is because if you try to put the next electron on it, the repulsive force is too great compared to the attractive force. And so it'll just blow apart.
Gotcha.
Okay. So there's another property of the electron that gives it gives the electron ability to act like a magnet. And this is called spin. It's an intrinsic property that has no mechanical analog. You can't really compare it to anything. However, spin has the same properties as angular momentum. So just like an electron orbiting an atom can produce a magnetic field, the spin, the intrinsic spin itself, can produce a magnetic field. Spin is innate with any quantum particle. So an electron has a spin of 1/2. That's the quantum number assigned to it. Okay. A proton also has a spin of 1/2 assigned to it. And there's other particles that have spin 0. So they won't have any magnetic properties. But really, it's the electrons we want to focus on. And again, if you have an atom like helium, the spins of the electrons will align so that, or they will align against each other so that the magnetic field will cancel out. Okay, you can have electrons with what are called spin up and spin down. I'll use that term.
Can you explain what spin is?
All I can tell you, if I give you a mechanical analog, it's wrong. You will see high school teachers give a mechanical analog of spin. Okay, the reason why it's called spin, because it has the same units as angular momentum, but it has nothing to do with an object rotating. It's something the electron is born with that you cannot give a mechanical analog to. Okay, that's really all I could say. And it could be because we don't have a good enough understanding of what spin is that we can't give a good explanation of what it is. You'll see people say, oh, it's like the spin of the Earth. No, it's not. Because the electron's not spinning. Okay? It's a quantum number. It's a quantum number associated with the electron or any quantum particle. And that quantum number times another number that pairs the quantum mechanics gives you angular momentum. But spin itself, we got to be careful. There's spin quantum number and spin angular momentum. And I'm referring to the spin angular momentum. The spin angular momentum is intrinsic of the electron.
Professor.
Yes?
So, like when we say that the helium has electrons which cancel each other's spin, then what happens to the spin of the proton? Like, doesn't that have any effect on the magnetic field that it can produce?
Well, they're in the nucleus, and so they really don't have a big effect. And they're really not doing they don't have any much motion. It's the coupling of the spin with the angular momentum that causes the magnetic field.
So does the spin of the electron enhance the magnetic field produced by the revolution, or does it decrease, or does it decrease its magnitude?
It will enhance it. So now I need to let me continue further. In a atoms have a bunch of electrons, though, right? And so only certain atoms are capable of acting like magnets. Those that have a shell that's half filled. There's a bunch of atoms where the shell is half filled. In other words, the electrons are unpaired, meaning that their spins are, you have a bunch of electrons that are spin up. So collectively, if you look at all the elements in the periodic table, there's a bunch of them that have half-filled shells that act like magnets. But when you talk about a magnetic material, it's different, because those atoms then have to form crystals. And those atoms have to come together to form crystals where the electrons in each atom essentially align in the same direction. And they form these things called domains. So you'll have a group of millions of atoms that have their spins aligned pretty much in a particular direction. So you have a chunk of material, and they have these domains. These are microscopic, where their spins are aligned in a particular direction. Now, we also need to have the spins of each of these domains to be aligned in the same direction in order for this to be a permanent magnet. And it turns out there's only 4 elements in the periodic table with which we can actually do that. There's iron, cobalt, nickel, and gadolinium. These materials can make permanent magnets. Okay, you can make them into permanent magnet. You still got to work with them to make them permanent magnets. Okay, but these 4 you can make permanent magnets with them. Of course, there's also other materials like the material that makes up this magnet called alnico. Okay, this is an alloy. You can make that into a magnet, but that's more complex. So there are also alloys you can use to make permanent magnets. But these are the elements basically that are used to make permanent magnets. But you still have to work with them because you have to align the domains, for example, for iron to be a magnet. Okay, if you just get a piece of iron, it's not going to be magnetic. You actually have to align the domains in the material to make a magnet.
So is it because it is easy to work with these compared to others that we make these as magnets and not the others?
Well, because they can form domains where the spins are aligned.
Yeah, but we do work to make those domains, right? So is it easy to make the domains in these elements compared to the others?
Well, nature makes it easy. We don't make the domains, we align the domains.
So is it easy for us to align the domains?
Yes.
Okay.
So like chromium, it has a half open shell, but it's anti-ferromagnetic. When the spins always align anti-parallel to each other when you try to form a solid. So they don't form these domains. It's just that these 4 can do that.
So the nickel itself is not magnetic, or
It's not a well, let me say this. It is magnetic, but it's not magnetized.
Yeah, so there is the confusion, because when we worked with the metals in material science class, and iron was magnetic. Okay, we made those domains, right? But then, aligned those domains. But when we worked with nickel, it was always not magnetic. Like whenever there was even if there was an alloy of nickel, or even if it was simply nickel, then it always was not magnetic. Or do we just make iron? Do we just like align the domains of iron and not of nickel?
It depends. Was the nickel put in a magnetic field ever? In a large magnetic field?
No, it was just tested with a magnet.
Okay, it was just tested with a magnet, so you brought it near a magnet and nothing happened?
Yes.
That's strange. Yeah, that's strange that the nickel didn't do anything.
Actually, when we did that, it was actually specified that if you have a nickel alloy or if nickel, you would not find it to be magnetic. So I'm kind of confused, like.
Well, the alnico does have nickel in it, and maybe it needs some impurities in it. I'm not familiar with that much with using nickel just as a magnet. I've seen this and this being used as a magnet. Rare, I mean, and some rare earth materials, but the rare earth materials are usually combined with something else. Okay.
So I didn't quite catch, what does ferromagnetic mean? Does that mean you can make a magnet out of it?
You can, you can magnetize it.
Okay, wait, like permanently or
Yeah, if you
temporarily?
if you take a piece of iron and you put it in a large magnetic field, you can align the domains so it becomes a permanent magnet. Well, I mean permanent in the sense it'll stay like that for a long period of time. Eventually, the domains will go out of alignment, and you know it won't act like a magnet anymore. I mean, I've gone in the lab in the stock room with one of these magnets, and this says North Pole and South Pole, and I've gone in the lab, and these don't do anything anymore because they're just laying around. I've also seen these where the North Pole and the South Pole are flipped. I've actually gone into classes with one of these to do a demonstration thinking that the North Pole is the North Pole, and it wasn't. So you do have to, every once in a while, put these kind of materials in a large magnetic field so that they stay magnetized. Something that's magnetic means it's capable of being magnetized.
Oh, okay. Thanks.
Okay. But here's the thing. The spin is responsible. My goal here was just to say that the spin is responsible for the magnetic field. The electron spin is responsible for it. Okay? If you try to understand where spin comes from, you'd actually have to go into quantum mechanics. And when you take Physics 215, at the end of Physics 215, you learn something called a Schrodinger Equation. And you solve it. But the Schrodinger equation does not give you anything involving spin. You got to take it one level higher. You got to write the relativistic version of the Schrodinger equation. It's called the Dirac equation. When you solve that, spin comes out of that. So that says that spin is a relativistic effect. Okay, that's the first thing. Now here's one involving electromagnets. I'm going a little bit too much into this, but anyway, so permanent magnets, again, are due to spin, and spin is a relativistic effect. Now let's consider the following. And this is one of the videos I have in the modules. And since we've done relativity, you can understand this. Here's a wire. Okay? And let's say we have a bunch of, I'm going to just draw it this way. this is not accurate, but the wire has a bunch of positive charges and a bunch of negative charges. And on average, what can you say about the total charge of this wire? It's neutral, right? The charge is on average neutral. Now let's run a current. Let's hook it up to a power supply. So that the electrons move in this direction at some constant velocity. Okay? So the electron's moving from left to right. On average, this thing is still neutral, right?
Yeah.
So let me put a positive charge here. And let's move it this way. Positive charge moves that way. It sees this neutral wire. It experiences no force, correct?
Right.
Now let's go in the reference frame of the positive charge. Let's make this a little bit easier for us to understand. Let's assume that this velocity and this velocity are the same. Let's assume that the velocity of this positively charged particle is the same as the velocity of the electrons in the wire. Okay? What does this observe?
Length contraction between the positive charges.
Yes, so these positive charges get contracted. So you have a higher density of positive charge than you do of negative charge. So what does that mean?
There's a net force inside the wire, or net field.
There's an electric field, right?
Yeah.
So what is this thing going to want to do? It's going to want to go like this. This particle is going to experience a force, a repulsive force. Isn't that true?
Makes sense to me.
Right? I mean, but wait a minute though. How can it be that from us who's standing here, we look at that charge and it's not experiencing a force, it's not experiencing a repulsion, but someone sitting on the charge experiences a repulsion? How can that be possible? That doesn't make sense, right? Even special relativity doesn't make sense. If you have an acceleration, you got to experience it in both reference frames. So what's happening? Well, what we're missing here is the fact that there is a magnetic field. These electrons are moving. There's a magnetic field created by this wire. Okay. That magnetic field produces a force on this charge in that direction. And we can determine the direction of this force later on today. So
are we saying that it only sees the contraction of the positive charges and not of the negative charges?
well, it's moving at the same speed, right?
Yes. But then, so the negative and positive both are moving in the wire, right?
No, the positive is not moving, right? The positive charge doesn't move in a wire.
Oh yeah, okay, sorry. Yeah, okay, they're moving at the same speed, so we don't see them to be contracted.
Correct. We only see the positive charge contracted.
Oh, okay. Mm-hmm.
Okay?
And then doesn't the electric field which is produced by the negative charge and the electric field which is produced by the positive charge, because still they are charges, so does that somehow cancel something because they're in opposite directions?
Yeah, but these are closer together though, right?
Yes.
So they're bunched, so it's going to produce a bigger field, isn't that true?
Mm.
So you're going to have a net repulsion.
Mm-hmm.
Right? And so this thing is going to be repelled by this excessive charge, because you're going to have a higher charge density of these guys than these guys.
Mm-hmm. Okay.
And that's what causes the repulsion from a person moving with the charge. But for us, we have to observe of repulsion also. And what answers that question is the fact that the moving charge in a wire produces a magnetic field. The magnetic field is basically an electric field as viewed from a different reference frame. That's all it is. So magnetism is really a manifestation of relativity.
Is it just like electric field when the charges are moving?
Yes, it's an electric field yeah, you can say it that way. It's the electric. It's an electric field. I would say it's an electric field from a different reference frame. It's the observation of what you would measure in a different reference frame. You would actually measure a magnetic field instead of the electric field.
So because the protons and electrons are very small, so they can travel in high speeds. But
actually, the electrons are moving very slowly.
Yeah, because they're in wire, so okay. But then if you have...
There's so many of them. That's what makes the force bigger. That's what makes it effective, because there's so many of them.
If you had a bigger charge, like simply a bigger ball of charge moving, like there is no relative effect there, right? Because...
I'm sorry, if you have
like a bigger ball of charge and it is moving in the same fashion, but at a very low speed, would you still experience the same effect on the charge outside that space?
You mean a big charge like this?
Like if there were bigger balls and in the similar fashion to the electrons in the wire.
Okay, you mean there was bigger charges in here?
Yeah, but they would not be in a wire then, because they would be too big for the wire.
Okay, yeah.
So would we experience a similar effect on the outside charge? Because if we say that it is a manifestation of the special relativity, then if there are bigger balls of charges moving at very low speeds, would you experience the same effect on the charge outside?
But you mean this thing going by me?
Yes.
Yeah, I would experience the same thing, right?
So then, is there still special relativity there, even though the balls are very big and the speed is very less?
Well, the effect is going to be much smaller, right?
So can we say that there is essentially no deflection?
Are we talking about this one or which one?
Yeah, the effect on that outside charge due to those big balls moving at very low speed.
Yeah, if it's slow enough, because the effect depends on V over C. If this is low enough, you probably won't be able to measure the deflection. It depends on this. In fact, I think it's this squared, the denominator squared. As long as, if V is small enough, you're not going to see it. But in this particular case, there's so many of them. The electric field is pretty strong, that the effect is not going to be negligible. But if you have large objects moving at slow speeds, you might not see the effect because there's probably not a lot. You're not going to be, the density of object is going to be small. Okay, so I kind of need to move forward, sorry. So my goal is to say that, my goal here was to just tell you where magnetism arises from, and that it is a manifestation of relativity. That's really what my goal was here. So I want to say a few more things about the properties of magnetic fields. And if you have questions, you can ask me at the end. I have a picture of how you can map out magnetic fields. I have a bar magnet, and all you need is a compass. And you can use a compass to map out the magnetic field due to a bar magnet. And the green circles with the yellow arrow in it is the compass. The arrowhead is the north part of the compass. Okay? And the arrowhead tells you the direction of the field. And so this is where we get the fact that the field lines go from the north pole of a magnet to the south pole of a magnet. And the figure on the right shows you a picture of what the field lines look like. So imagine those field lines and rotating them about an axis that passes through the longer side of the magnet. Okay. I want to say a few things about the differences between the electric and magnetic fields. I want to progress to that. But here's another picture showing you magnetic field lines due to a current carrying loop of wire. And the direction of the magnetic field at any point in space is basically tangent to one of the field lines. Where is the field line greatest? This is a refresher on field lines. Where's the field lines? Where's the magnetic field greatest? In that picture.
On the outer surface?
Well, base it in terms of the field lines, your description of the field lines.
In the middle.
What's special about the middle?
There's more field line, like the density of field lines is higher. They're closer
Yeah.
together.
And you know, the same idea as with the electric field lines. The denser the field lines, the greater the field. Here's one due to uniformly spaced, two closely spaced magnets, you can produce a uniform magnetic field in a region of space. Look at how uniform the field is in the middle. So if you want to creating a uniform magnetic field is difficult. Okay? And so this would be one of the ways to do it. Because the field lines tend to form closed loop, it's very difficult to produce a uniform magnetic field in practice. The Earth itself is a magnet. What do you notice in that picture?
That the geographic south pole is actually the north pole on the magnet?
Yes, the Earth itself is a magnet, so be careful. The geographic south pole is the north pole of the Earth's magnetic field. Okay? The geographic north pole is the south pole of the Earth's magnetic field. The magnetic field is not strong. It's not a huge magnetic field, but it protects us from charged particles, which I'll talk about a little bit later. Yeah, it's very confusing, right? We say it's the North Pole because the North Pole of the magnet points that way. Yeah, it does do that. It does flip about every, 250,000 years? Something like that. The poles do flip, and they're huge time scales. And, that's due to, the theory is that this magnetic field is due to the currents. They're called, they're currents of positive or negative charges within the molten material at the center of the Earth, because that stuff is always flowing. That's the theory. Now, people have used the compass for many, many years to basically get around the Earth. Does anybody realize the issues in dealing with the compass? What are some problems dealing with a compass?
So, like, if you were transporting some precious metals, wouldn't that throw off your compass?
Yeah, you wouldn't even have to transport anything. There are certain locations on the planet where there's enough magnetic material near the surface that it can throw your compass off by 90 degrees. It turns out that if you take a magnet, a compass, okay, and you point it, point it north, it might not really be pointing geographic north. It might be off at an angle. The angle between the compass north and geographic north, that angle is called a declination angle. And it varies all over the surface of the Earth. It can be as much as 90 degrees.
Where on Earth would, like, do you know, like, where this would be, like, a specific, like, example?
I forget. I mean, you can look that up. I mean, who is it? One of the geographic services, they will actually tell you. I think even on Wikipedia, you can actually look it up where it's 90 degrees. I think here the declination angle is maybe 10 degrees. But where you're by places where you mine iron and stuff like that, when you get iron, it's going to be a lot higher. So you do have to be careful. There's a declination angle, and you can measure with one of these things. For example, this is a tool you can use to measure the declination angle. So what you got to do is put it in the horizontal plane and try to look at the difference between, although you'd have to aim this, you'd have to figure out where true north is. Okay, you have to figure out what true north is. And you can measure the angle between true north and where this guy points. There's also something called a dip angle. Because when you're using a compass, you're measuring the component of the Earth's magnetic field that's tangent to the surface of the Earth. The magnetic field of the Earth also has a component that's perpendicular to a plane tangent to a surface to your location. So for example, if I drew the Earth, and you're standing here, your compass measures the direction relative to in the plane of this, in this particular plane. But the Earth's magnetic field also has a component this way. And this angle is called a dip angle. And you can easily measure it with one of these.
Wouldn't we expect that angle always to just be near 90 degrees if it's just going to point inwards towards the center of the Earth?
No, it's around. It's not directly at the center of the Earth. It just depends on because the Earth's magnetic field is dependent on like molten nickel and stuff that's within in the core. Right, here's a magnet that's very small that I have essentially on a, hold on a second, on a universal pivot. And this can easily measure the dip angle. This thing can rotate in any direction. Can you guys see that? Very difficult, I guess. Maybe I'm too close. You guys see that okay or not? You can actually measure that dip angle. In Sacramento, it's like 32 or 34 degrees. I forget the exact number. So Earth's magnetic field is basically has a component perpendicular to a plane, perpendicular to the plane of your compass, and then one within the plane of the compass. Those two components will give you the total magnetic field of the Earth. Okay, and you can actually have experiments where you can actually measure the magnetic field vector of the Earth. We can't do it here. I'd have to ask the geography people, where is true north? If I had a way for us to designate true north, we can actually do that in lab. Although we'd have to be on campus. There's a lot of interesting facts about magnetic fields. Of course, we don't have time to go through all of them. So, I want to say something in relation to the magnetic flux. Just like the electric flux, we can define the magnetic flux. This is section 30.5 of your book, which is the integral of the magnetic field dotted with the normal to the surface times dA. The unit of the magnetic flux is called the Weber, also known as a Tesla meter squared. A Tesla is the unit of magnetic field. Oops, something missing. If you integrate this around a closed surface, you get 0. That's because field lines form closed loops. So this is a reminder regarding field lines before we finish talking about Gauss's law and magnetism. Electric field lines begin and terminate on charges. Electric field lines extend to infinity for a single charge, and the electric flux through a closed surface is proportional to the charge. The charge enclosed. But magnetic field lines form closed loops. The number of field lines entering a closed surface equals those leaving the surface. The magnetic flux through the closed surface is 0, and that's because magnetic charges don't exist. There's no such thing as a magnetic charge. All magnets come in as dipoles. If you take a magnet, it comes with a north pole and a south pole. If you cut it in half, you still get a north pole and a south pole. The electron intrinsically is a magnet because of its spin, and it has a north pole and a south pole. Is it possible to get an analytic for the magnetic field of like the Earth? Yeah, you just have to model it in a particular way. The problem is, Damien, you have to assume a uniform Earth. The problem is, the Earth is not uniform in the material is not uniform, right? Wherever there's locations where you have iron deposits and things like that, that's going to make it vary. But I mean, if you want to use a very what physicists call a zeroth approximation, you can do that. You just won't be able to get all the variations. So the integral of the magnetic field around a closed surface is 0. There's no magnetic charges. That's Gauss's law for magnetism. So I should say this because we're moving towards this. We're moving towards a very important idea at the end of the semester. These equations are four very important equations that occur in physics. These are two of what are called Maxwell's equations. Okay, we're going to see two more later on, and they're going to come in this unit. Okay, so three of the four Maxwell's equations are essentially in this unit. Okay, so these are two of the four equations that we use to describe fields, most of anything in this course. Okay. So, here's an interesting question. Suppose a magnet designer tells you that he can produce a magnetic field B equals x over a I hat in a vacuum that points everywhere in the x direction. And the thing is the question is this field possible? What do I have to do to prove that this field is possible?
That the flux is equal to 0?
I have to show that the flux is equal to 0. If you had Calc 3, there's a very easy way to do this, but unfortunately we can't use the methods of Calc 3. Okay, so I got to calculate the integral of the flux through every surface. How many surfaces do I have?
6.
6. So I got to do 6 integrals, right? Or not?
No.
Why not 6?
Because 4 of them are perpendicular to the...
That's right. Okay, it's not a great picture. Sorry about that. That's really bad. Hold on a second. I drew it differently from the book, from the PowerPoints. Hold on. One more try. Okay. So let's make this the x direction. Let's make this the y direction. This is z direction. And we said that B is B naught x over a I hat. Okay. So each side is a. So which side should we be concerned with? Because we want to take the integral.
The ones in the YZ plane.
Yeah, so we want to look at that one and this one, right?
Yeah.
Because this one points in the minus I hat direction, and this one points in the I hat direction. The other four, the top product is going to be 0, right? Isn't that true? If this direction is a z direction, I dot z is what? I dot k is what?
0.
So this one, the one behind it, the one above, and the one below don't contribute at all. So just the one on the left and the right. Now let's take a look at the one on the left. What's x on the one on the left side?
0.
It's 0. So far, so good. 5 sides give me no flux. Right? 5 sides give me no flux. What about the 6th side? What does this give me?
B naught.
What's x on this side?
A.
So then I got to integrate B naught over the area. So my total flux is this. The other 5 sides give me no contribution. So what does that say? about the designer.
He's lying.
The designer's lying to you. You cannot create that magnetic field. Okay. Now this is to me is the really the most important part of my lecture today is what happens when you have a charged particle in a magnetic field. Let's say you do an experiment and you place a charged particle in a magnetic field. What happens to the charged particle? It's going to experience a force if it's moving and it has a component of its velocity perpendicular to the magnetic field. Okay? If you put a charged particle in a magnetic field, there's no electric field. That charged particle will only experience a force if it's moving and its velocity has a component perpendicular to the magnetic field. What does that suggest mathematically? Oh, by the way, the force itself is perpendicular to both V and B. Yes, Chase, it's basically a cross product. The actual force on a charged particle in the magnetic field looks like this. So we determine this by experiment. By experiment, we can obtain that the force is given by this expression. So the force is perpendicular to both V, and B. B stands for the magnetic field.
Professor?
Yeah.
When we said that magnetic field is like an electric field, but from a different perspective, then why doesn't the charge experience a force due to that field, even though it is not moving? Because generally a charge experiences force in an electric field, right?
Yes.
But then if the magnetic field is like an electric field, but in a different frame, then shouldn't it also experience force even though it is not moving?
Well, there's nothing that says that the field has to be, there's nothing that says that if the particle's not moving, it's experiencing an electric field.
In an electric field, the charge moves, right?
Yes, but what you're saying is if the charge is not moving, then it's experiencing an electric field, right?
No, I was saying that if a charge is placed in the magnetic field and we say that magnetic field is an electric field but in a different frame of reference, then shouldn't the charge experience a force due to that new electric field?
But what we're saying is the magnetic field is I guess it has different properties though.
I was just wondering that we said that it is like an electric field but in a different frame of reference.
Right, but it experiences physically experiences a magnetic field, not an electric field.
Mm-hmm.
So it's not going to experience the electric field at all because what it sees is what it would measure is the properties of a magnetic field, not the properties of an electric field.
So in different frames of references, the electric field has different properties.
Correct.
Okay.
So when you say it's a completely different behavior, right? I mean, the field lines circulate. Electric field lines don't circulate, right?
Yes.
Okay, so it's completely different. It's a completely different effect.
Mhm.
So you can't say it's going to experience the effect due to electric field. It just becomes a magnetic field.
So do we know why it doesn't experience a force, or did we just determine with experiment that this is what happens?
That it doesn't experience an electric field.
No, did we have any, did we do any calculation or anything like that which tells you that there is no force if the charge is not moving? Or did we just experimentally find
Oh,
that?
this is experimental.
Yeah.
This is not derived.
No, is there an explanation for why that happens, or is it just observation?
It's just observation, just like Newton's second law.
Okay.
Okay. Okay. If you put a charged particle in electric and magnetic fields, hold on a second, I want to skip this video. If you put a charged particle in electric magnetic fields, then the total forces it experiences is given by the following. We call it the Lorentz force. I still need to say some more about this cross product, but this is the total force a charged particle will experience in an electric and magnetic field. This equation plus Maxwell's equations that we'll talk about summarize everything in this course. Maxwell's equation relate electric fields. This one relates the forces to a charged particles due to the fields. Okay.
Electric field is a vector, right, in that equation?
Oops, yes. Thank you.
This cathode ray tube injects a beam of electrons into a volume of very low pressure gas. If we apply an electric field between the plates, the electrons, being negatively charged, deflect toward the positively charged plate. Next, we turn off the electric field and turn on electromagnets to create an identically oriented magnetic field. Now the force acts at right angles to the direction of the field and to the direction of the beam. If the field is reversed, the beam curves in the other direction. The magnetic force is proportional to the magnitude of the charge, to the magnetic field, and to the particle's velocity with respect to the field. The force always acts at right angles to both the field and the velocity vectors. The force reverses direction if either the field or the velocity changes direction, or if the charge changes sign. If both electric and magnetic fields are present, the charge is influenced by each separately. This equation is the complete expression of the Lorentz Force Law.
So let's focus just on the magnetic force. Let's set the electric field equals 0. And let's take a look at this term. Okay, let's look at this part of the Lorentz Force Law and say a few things about it. We're letting E equals 0, and let's write the magnitude. This is a cross product. You guys remember how to evaluate a cross product? You did this in 205? Okay. So the magnitude then is going to be the magnitude of Q times the magnitude of V times the magnitude of the magnetic field times sine of theta. The angle between V and B. Okay. If we can measure the force on the charged particle, then we can actually quantify what the strength of the magnetic field is, which is going to be F over Q V sine of theta. What are the units of this? Well, it's going to be a Newton per Coulomb meter per second. Of course, this has no unit. Sine theta doesn't have any units. Okay, so this is going to be a Newton times a second over a Coulomb meter. But a Coulomb per second is an amp. This is also known as a Tesla, like the car. Okay, so that's the unit of the magnetic field, so Newton amp meter. Okay. Tesla is actually a fairly large unit for a magnetic field. There's also another unit for the magnetic field called a Gauss. One Tesla is 10,000 Gauss. The size of the Earth's magnetic field is approximately half a Gauss. Of course, this varies, but this is an approximate value. Okay. The size of the Earth's magnetic field is about half a Gauss. And so, by measuring the force, we can quantify the magnetic field in this method.
Wait, so I'm a little confused on that earlier equation where it was the force on the charged particle and electric and magnetic fields. Is that when you have like two going at the same time?
That's if you have the electric field that's not zero and the magnetic field that's not zero.
Oh, okay. So this equation's only for if the E equals 0 then?
Correct.
Oh, okay.
So how do we determine the direction of the force on a charged particle? Well, we use something called the right-hand rule. Obviously, we can do it this way, but the cross product really involves something called the right-hand rule. The cross product defines a third vector that is perpendicular to two other ones for a right-handed coordinate system. Because basically, if you don't choose a right-handed coordinate system, you just say, find a vector that's perpendicular to two other ones, you can find two. Okay, so we use a right-handed coordinate system just to pick one. So how do we determine the force on a charged particle in a magnetic field? So we got to think 3D. So let me draw a three-dimensional coordinate system. And I'm not going to label X, Y, and Z for now. What I'm going to do is this. Let's say we have a particle moving to the right. And the magnetic field is out of the board. I want to use the right-hand rule. So I take my right hand, hold on a second. I gotta get rid of one thing, or else you can't see me. Okay. So you take your right hand. You guys can see me okay?
Yes.
You put them in the direction of V. You point your forefingers in the direction of V. And you curl them towards the magnetic field. Now, my hands don't bend backwards. I don't think your hands can either. So I got to flip my hand or my palm around and then curl them towards the magnetic field. Which way does my thumb point? It's pointing downward, so that force is downward. Whoops, that one's done. Okay, these markers seem kind of light, but we'll see. Can you see that okay?
Yes.
Or is it or is it not bright enough? So anybody have any questions on that? You point your fingers in the direction of V. I gotta flip my thumb, my palm over because I can't bend my fingers backwards. Curl them towards the magnetic field. Your thumb points in the direction of the force. Any questions or concerns?
I had one question.
Okay.
It is just that if the velocity is in one direction, then for our fingers to curl in a reasonable manner, the electric field can be only in a certain, the magnetic field can be only in a certain direction.
This for this given example, I can change the direction of the magnetic field. I'm not sure I understand your question. I mean, if the particle is going that way and B is into the board, then I take my fingers, pointing towards the velocity vector. I gotta flip my hand over again. Curl them towards B, and the force is downward.
And if the magnetic field was opposite the direction of the velocity?
Then it's zero, right? Because then it doesn't have a component perpendicular to the velocity vector.
Yeah.
Okay.
Yes.
And you only really use the right, to me, you only really use the right hand rule if V and B are perpendicular to each other. If V and B are not perpendicular to each other and you want to find the direction, I got rid of, you use the determinant. I mean, if you're going to get something that has a component, a force that's, like in some weird direction, it's much harder to use the right hand rule that way. So let's demonstrate this. I'm going to demonstrate the right hand rule. I want you to see a real charged particle moving.
Professor?
Wait, oh, sorry, go ahead.
Well, I was just asking that if the magnetic field was, instead of being in X, Y, or Z direction, if it was uncertain.
Yeah, then, like I was saying, you probably want to use the determinant.
Yeah, because then the force is in one direction only, no matter in which, like at which angle the magnetic field is pointing.
Only the perpendicular component matters. So you just break it into a vector and use the pieces that are perpendicular.
Yeah, you can do that too, right? You can just you just choose the ones that you know are going to contribute.
So it doesn't matter at which angle the magnetic field is, the force will always be in one direction.
It's going to be, well, you want to choose the velocity component is perpendicular to the magnetic field.
Yes, but the direction will remain the same. If, suppose like the figure that we have on the board, if the magnetic field was, suppose in the quadrant on the right, then if you curl your finger, still the force is in the downward direction, right?
Yeah, so let's say the magnetic field has this, and then the velocity so these two components and these two, they would produce a non-zero force, right? The cross product of these two and these two. But not I cross I or J cross J. But again, if it were me, I would evaluate using the determinant. Why do it the hard way if you have a way to do it with the determinant?
Wait, what was the determinant again?
You remember from physics to was it physics? Did you do 205? When you did torque and angular momentum.
Oh, is that just the method of doing the cross product?
Yeah.
Oh, okay. Because I knew how to do the cross product. I just forgot the terminology.
Okay, let's focus on this. You see the green light?
Yes.
Okay. What is that green light? It's electron. It's basically an indication that I have a beam of electrons going through that tube. Why is it green? Well, the electrons are colliding with whatever gas is in there. The gas molecules, the electrons in the gas molecules get excited to a higher level state, and they want to return to their original state. When they return to their original state, they give off energy in the form of light. And in this particular case, it's this greenish light. The electrons are going in that direction. Okay? And what I'm going to do is I'm going to take a magnet and I'm going to bring it near the electrons. I'm going to bring the north pole of the magnet. The field lines go from north to south. So I'm going to bring the north pole, I'm going to put the north pole of the magnet behind. So the magnetic field is pointing towards us, or towards you folks. So I'm going to use the right-hand rule. I have the magnetic field pointing towards you folks. The velocity is to the right. And what does this say? Oops, you can't see it anymore. Do you guys remember that it said that the force has to be downward?
Yes.
Okay, let me see if I can, although that green is hard to see. Oh, you can't see it. So the force is downward. You guys ready? We're going to verify the laws of physics here.
Wouldn't the force be upward because the charge of the electrons is negative?
Oh, is that the case?
I have no clue. That's why I'm asking.
So what did I assume here when I did this right-hand rule?
That the charge is the same sign as the direction
I assume that the charge is the same sign, right? And these are electrons. So that means they're not going to go down. They're going to go up, right?
Yeah.
What happened? You see what happens to the beam?
It's going up.
Okay. The beam goes up. In fact, I think it works better with this magnet.
It's kind of cool.
All right, the beam goes up. So you actually can see the effect of, like, I hate talking about this stuff without you being able to see what the heck the electrons are doing. In fact, I forgot a piece of this equipment. I had to go run back to campus to get something so I can make this work today. Okay, so you can see the beam bend upward. Okay? You can see the beam bend upward. And you're right. That was very observant that I didn't say anything about the fact, what do you do with the left? What do you do with a negative charge? So if I have a negative charge, I still apply the right-hand rule and then just flip this vector over. That make sense?
Yeah.
Yes, no? Okay, so again, if it's a negative charge, I still apply the right-hand rule and then flip the vector over. And some people will say, well, what if I use my left hand? Yeah, the left hand will work, but then I don't want to get confused with right-hand rules, left-hand rules, etc. Okay, this is one of many right-hand rules you're going to be dealing with in this unit. There's at least 4. So it's fun when you guys are on campus and I give this exam and everyone's doing all kind of stuff with their hands during the exam. Let me turn this off before I get zapped. Okay. There is, and normally if we were on campus, I would have another device where I would make the electrons go in a circle and you would be able to see that, but I didn't want to bring that because that involves me bringing an expensive tube home and I want to break it. So I think what I'm going to do in the lab, because we're kind of over, I'm going to talk about the motor lab, which won't take me long, and then I'm going to talk about the motion of charged particles in a magnetic field. I'm going to say some more about this. Okay, you probably have enough to do at least more than half the homework assignment right now. But when we talk about this in lab on Thursday, I'm also going to show some examples. The main examples, especially for those of you who are in chemistry, is to discuss the mass spectrometer. Okay, I'm going to do that in the lab on Thursday. Okay. All right. Were there any other questions I can answer regarding the relativistic effect? I know you guys had a lot of questions on it. I didn't realize I was going to get that many questions on the origin of magnetism.
I have a question.
Go ahead.
We were talking about that example where you had the ring, and we said that the magnetic field is strongest between, like, on the inside of the ring because of the density of the field lines.
Yeah.
Are we assuming the ring's not a conductor? Because didn't we discuss the electric field and there would be 0?
Well, the ring it is a conductor, right? Because it was carrying a current.
Right. I guess I'm just confused about where the field lines would begin and end on that surface in that case.
Well, I plotted the magnetic field lines. I didn't plot any electric field lines. Magnetic field lines don't have a beginning or end.
Okay, I guess I just thought that they began or ended on the I thought they began or ended on the actual magnet.
No, they just go. I know. On a permanent magnet, you mean?
Oh, okay. Is that what a permanent magnet is? Is that it goes?
You mean like? Hold on. Let me go back a couple of slides. This is the one you were asking about, right?
Yeah.
Yeah, and this is not a permanent magnet. This is just a loop of wire carrying current. But the field lines go through those magnets.
Oh, I see.
I don't know if you can see it on the right.
Yeah, I can.
Okay.
Yeah, that answers my question. Thank you.
Yeah. Yeah, they all form closed loops. That's the big difference between the field lines, the electric field lines, and magnetic field lines. That's the main difference. Other questions?
I have a question.
Sure. Yeah, go ahead.
When we have the magnets like in the Earth's core, and we say that okay, those can affect the the compass direction. So does the magnetic field of the Earth make the domains aligned for those metals?
Well, it's not really well understood exactly what's producing. I mean, there's a theory that the magnetic field is due to the motion of charged ions circulating inside the liquid within the Earth. In other words, it's an electric current.
Yeah, but when we say that near the mines, or if you have like iron, that can affect the direction of the compass. So that would happen if that metal had a magnetic field of its own, right?
Yeah.
And that magnetic field would be there if it was acting like a magnet. And it would act like a magnet only if the domains were aligned.
Yes.
So does the domain align due to the Earth's magnetic field when it is inside Earth? Because we did not align them ourselves, right? They're already inside the Earth.
But if you put a magnet near iron, they're going to attract each other, right? Whether the domains are aligned or not.
I thought that we said that if the domains are aligned only then something happens.
It's magnetized.
Mm-hmm.
Right? I mean, we're talking about something that's magnetized.
But it can still attract things,
correct,
even though it is not magnetized.
That's right, that's right.
And what was the reason for that attraction?
The attraction between
iron and a magnet.
Well, you can have the magnetic dipoles and the iron orient themselves. Well, it's like I'll give you the same thing as, let's say you rub a balloon on your head and you put it on the wall. Why does the balloon stick to the wall?
It was charged, right? When we rubbed it, there was static charge on it, and then it attracted the opposite charge in the wall.
Yeah. So if you have a magnet and you put it near something that's iron, what's going to happen is it's going to attract the opposite. So if you put the north pole of the magnet near the iron, it's going to reorient the dipoles in the iron so that the south pole is directed towards the north pole of the magnet. You're reorienting your dipoles. It's the same idea.
And this can only happen in certain elements.
Yes, these elements that have domains.
So but then is the domain the same as the dipole?
The domain is a bunch of dipoles that have a particular orientation. So I guess I should have said the domains would orient themselves.
And these are due to the unpaired electrons.
Yes.
But then if certain elements have unpaired electrons, not all of them can be magnetized, but all of them will be attracted to a magnet?
Not all of them. It depends. I mean, there's some that will be repelled.
Mm-hmm. Yeah. Okay.
Those are called diamagnetic materials.
But all of them will experience a force.
Yes, but of course these forces would be really small.
Mm-hmm.
Right? There's materials that are called paramagnetic. There's materials that, and typically I don't have time. I don't typically don't get into them in this course because of time issues. But one could talk about paramagnetic materials, diamagnetic materials, ferromagnetic materials, ferrimagnetic materials, and a lot of that I just don't have time to get into. And the understanding of how they work, you have to go at the microscopic level, the quantum mechanical level. I don't know if that answers your question, but I mean, but yeah, those materials that are not ferromagnetic, that don't have domains, can still react to a magnet. Sometimes they'll repel and sometimes they'll attract. But the effect is weak. You'd have to see the effect in a very strong magnetic field.
And in the cathode ray tube, is the discharge continuous or is it pulsating?
This one is continuous. I have an alternating current source.
Mm-hmm.
So yeah, it's a continuous. It's an induction. It's using the concept of induction, which you'll learn about in a couple of chapters from now.
But even though it is continuous, the electron gets the chance to come back to the lower energy.
Yeah, there's a collector on the other side.
Mm-hmm.
It's kind of like having a mini accelerator. I mean, that's really what it is. I mean, there's a person who does he does a video with who shows that the electron's going in a circle, and he has basically I think it's a DC power supply and an electron gun, and it's basically a CRT tube. This is not really a CRT tube. What you saw here is not really a CRT tube. It's called a Crux tube. With a CRT tube, you can have voltages, you can vary the voltages, etc.
And it is the same, like the CRT tube was the one that was used to discover electron, right?
Yeah, the one I showed you in the video.
Mm-hmm.
Yeah. I'll talk about that one a little bit on Thursday. Yeah, so that one, that was DC power supply in that particular case. You use DC at a fairly high voltage, high enough so you can ionize the gas that's in the tube.
And just one last question. It is for the lab.
Yeah.
Can you repeat the wording that you said before? Like, if the results do not show the verification of Kirchhoff's laws, then what was the line that we should write? That our results are not in agreement, or like?
Yeah, you can say they're not in agreement, and you can say there's probably, you can try to estimate why. You can try to figure out why. I mean, it's not going to be definite, but there's systematic errors in your experiment, right?
Mm-hmm.
So you can say that could be attributed to the systematic error. Usually, if your measured value is not within the range of the theoretical expression, or two measured values, their values don't overlap each other, that usually means there's some sort of systematic error that you have to account for.
So we should write that the results are not in accordance with the laws, and we should not write that it does not verify the law, right?
Yeah, you should just say it doesn't agree with Kirchhoff's law, and one of the reasons could be that and you can try to estimate what figure out what the systematic errors are.
Mm-hmm.
Obviously, in 205, it's easier. It's always errors. It's always friction or something.
Yeah.
But here it would probably be like, you take out the multimeter, for example.
Mm-hmm. Yeah.
For measuring current, that'll cause that can cause the discrepancy.
And should we like when we did the second part where we added a multimeter between points A and C, and then we used another multimeter to find the current through the power supply, should the current be less than part 1 because we introduced one more resistor in the circuit?
Should it be less than in part 1?
Yes.
Well, it's going to be it's going to be different, right? Because you have a different circuit.
Yes. But then it's like we introduced some new resistors in the circuit, right? Because the ammeter also has its resistance. And should the current then, should we expect it to be less than the current in part 1?
I have to think about it. I can't answer that off the top of my head. And the reason why is because part 1, your circuit looks like this. Part 2, your circuit looks like this. Right?
Mm-hmm.
So, I mean, it's going to depend on what these values are.
Aren't we using the same resistors?
Yeah, but isn't the configuration different?
Yes. Mm-hmm.
Yeah, but I don't remember off the top of my head the values. That's my point.
Because I could understand my results that I got for the voltages. The voltage across R3, it was lowered in the second circuit compared to the first. And I thought that because some of the current flows through the ammeter now, and there would be less voltage drop across R3 compared to the first one. So that could be the reason that I got a lower voltage
For this one?
R3. Yes. Because like the path diverges now into the ammeter.
You're going to have are you going to have a total higher current here?
Yeah, the voltage across that increased across R sub 2, and across R3 it decreased.
See, these two are in series. So the equivalent resistance of that one is this. The equivalent resistance of this one is this. So I have to compare those two.
Are we not considering the effect of the additional ammeter between points A and C?
No, because it's small, right?
Mm-hmm.
I'm assuming it's ideal.
Yes. Okay.
Okay. So I have to compare this to that. If this one is smaller, then you would have more current going in this one, right?
Yes.
Did you have more current here?
Yes.
Was this a bigger current?
Yes.
Okay, so that means this is smaller. Okay, so that means you will have
Could we say that because of the introduction of the ammeter, it provided a less resistive path for more current to flow, like something like that?
well, it does take away some current from this.
Yes.
Yeah. And is this one bigger then?
The voltage?
Yeah.
I'm sorry, I will have to
Okay.
see it.
But right, because I'm using what you're saying that this is going to be a smaller voltage because I have some current going through here. But then is the current going through R1 here the same as this one?
I think the voltage across R4, it increased.
It increased. What about these two? Are they the same or different?
R1, let's see. So the voltage across R1 also increased.
Okay, so it was higher.
Yes.
Okay. So this is higher, but this one went lower.
Yes.
See, if these two were the same, I can say right away. Yeah, then I can say, okay, yeah, this will get smaller. But because this has increased, it's just hard for me to make that. Just say, oh yeah, it's because you have some current going this way. You know, if you're trying to compare this circuit to that circuit, because they're completely different circuits.
Mm-hmm.
You see what I mean?
Yes.
And does this get smaller then? No, it's the same. Well, yeah. I mean, R1 and R2 are the same. So is this one smaller than this one?
Are you saying R2?
Yeah, R2. Because I forget the values.
So R2, it decreased.
It decreased. Okay. Because you have more current going through here, this circuit though, right? ISOBS is bigger here than it is there.
Mm-hmm.
Okay. So, I mean, in order to answer your question, for me, it's hard to say that. It's hard to say say anything definite because this number and this number are not the same.
Yes.
And I don't know if it's fair to compare those two circuits because they're different.
Yeah, I was just trying to make like some expectations to check the values that I was getting.
Yeah, I just... Because the circuits are different, I mean, by just putting that meter across, this changes everything.
Mm-hmm. And this lab is due on Thursday now, right?
Yeah, I'm going to change this once I'm done with this class.
Okay. Yeah, that was it for me. Thank you.
Okay. I'm not sure I understand your question, Jacob. The current plug. The current plugins. Amps or milliamps? Well, do you want more sig figs or less sig figs, Jacob? Right. The decision is, do you want to use more sig figs or less sig figs? But you also don't want to blow the fuse. So what is it about table 3 you're confused about?